part of this, we're just graphing and reviewing exponential functions. For this graph right here, I know that this is going to be an exponential growth. And the reason why I know this is an exponential growth is because the base is greater than 1. That's all that is. Also notice we have a limit right here. This graph is never going to drop below this line. And this line is a horizontal asymptote of y equals 0. And that horizontal line directly affects the range. If you guys notice right here, there's where this floor is blocked out. The lowest it could ever be is approach 0. Then it goes up to infinity forever. Now it does approach this, but it's never going to touch it. So your domain and range are never going to have brackets. We're never going to include values because it's either infinity or it's an asymptote that's included on that. On this other equation, I know that it's an exponential decay. I know it's an exponential decay because your base is less than 1. So if your base is less than 1, it is going to be a decay. Two more things that you can always tell if it's a growth or if it's a decay. Guys, if you notice, this graph is down on the right. So it's not pointing up. If it's not pointing up, it is not a growth. Over here, if you notice, this graph is up on the right. So there's the up arrow right there. I can very clearly see that that is going to be a growth. This is a picture of a growth up on the right. This is a picture of the decay down on the right. So you can also, just like we just mentioned, you can always tell if it's a growth or a decay based on the base. If the base is greater than 1, it's going to be a growth. If the base is less than 1, it's going to be a decay. Don't just look for fractions, though. 7 over 4 is a fraction, but it's greater than 1. Remember, if you change that to a mixed number, it'd be 1 1/4. So we know for sure that number 1 is a growth because the base is greater than 1. Remember, the base is what an exponent is raised to. So the base is always going to be raised to an exponent. That's the definition of a base. It's whatever is being raised by an exponent. So if you notice right here on number 2, only 2/3 is being raised. So only 2/3 is the base. So this is going to be a decay. And then over here, remember, only 7/4 is being raised to an exponent. Only 7/4 is a base. So 7/4 is actually greater than 1. So this is going to be a growth. And guys, just remember, here's some more description right here. Remember, your base is what an exponent is being raised to. And if there's more than one number, then your B value will be very clearly marked, either by parentheses or by an actual multiplication dot symbol. So lots of ways for you to be able to use those clues to define what the base is on a problem. On this next part right here, this is your general form where you can very clearly see HK and A. HK is actually not on the graph. HK is going to be the new origin. We're going to call it a starting point. It behaves like a new origin on a coordinate grid, and we'll talk about that. The transformations from the parent function are the same with all of the previous ones we studied, guys. H is going to be opposite. K is always added or subtracted at the end. If A is negative, it's going to be a vertical reflection. What's different now and what is new is the equation also shows us what the asymptote is. And remember, the asymptote is a boundary where the graph cannot cross it. So for exponential functions, your asymptote of y equals k, it is going to be considered like a floor where the graph cannot go past it unless it's a vertical reflection. Vertical reflections make y equal k a ceiling. That's the highest the graph is going to reach. So it's either a floor or a ceiling for an exponential function. Let's go ahead and take a look at the next page. On the next page, we just have another example of an exponential function. I know the exponential function is a growth by looking at the picture because it's up on the right. But I also know it's a growth because the base is greater than 1. So we certainly know it's a growth. Also notice that this graph has a floor right here. This is y equals -4. Remember, that's your asymptote, and it also plays a direct part in the range. So the lowest the graph can go is a -4, but again, the graph can go up forever. With exponential functions, we have the natural number e, which is a ratio that appears in nature. That's why they call it the natural number. It behaves like pi. It never ends and it never repeats. The main takeaway from this is that the natural number rounds to 2 point something, which means the natural exponential function is going to be a growth. Are there any questions on how to identify the natural function being a growth function? All right, let's go ahead and analyze some attributes here at the bottom of this page. So we're going to determine if it represents a growth or decay. We're going to state the transformations, domain and range, and the y-intercept. Guys, just so you know, it is going to be an expectation on your quiz for you to be able to solve the y-intercept without a picture. So you are going to have to solve for this algebraically. All right, let's go ahead and work through example 1. For example 1, we have a base that is greater than 1. The base is a 2. So if the base is a 2, I know that it is a growth function. HK is going to be a -4, -8. Remember, your H is always opposite from what is in the equation. Your transformations, you only have 2 transformations here. This graph is 4 places to the left. And then this graph has been shifted 8 units down. For your domain, guys, you can put in any number for an exponent. Even a negative exponent. Remember, that just means it's on the other side of a fraction bar. So your domain is -infinity to +infinity, but not your range. Your range, remember, is directly affected by your asymptote. And remember, your asymptote is y equals k, and the k value for number 1 is -8. Also notice we don't have an a value that's negative or anything like that. So this asymptote behaves like a floor. So once we've identified that it behaves like a floor, then we know that the lowest that this graph can get is approaching -8, but it does go up forever. All right, let's talk about the y-intercept. You do have to solve algebraically, so let's go ahead and let x be 0. So when x is 0, we're going to plug it in and just solve our work here. This is going to be 2. And then in parentheses, it's going to be 0 plus 4. And then minus 8. So this is going to be 2 to the 4th minus 8. And I think most of you guys have 2 to the 4th memorized now, right? Very good. So this is going to be 16 minus 8. And that's just going to give us a y-intercept of 8. Any questions on number 1? Let's keep going and take a look at our decay. We definitely know it's a decay because our base is less than 1. Our h value is going to be +1, +6. We only have 2 transformations. We don't have an a value in front of the base, so our transformations are just from hk. And this is going to be shifted 1 unit to the right, and it's going to be 6 units shifted up. Guys, your domain is always negative to positive infinity. Your range is going to be based on your asymptote. So remember, your asymptote is y equals k, so y equals 6. And again, this is going to behave like a floor because I do not have a vertical reflection. So I know that my range is going to start at 6, but it's going to go up forever. To solve the y-intercept algebraically, remember we're going to plug in 0 for the letter x. So for the y-intercept, it is going to be 1/2, and then in parentheses for your exponent, it's 0 minus 1, and then of course plus 6. That turns into 1/2 raised to the negative first power plus 6. So you can have negative inputs, you just have to compute them as positive. So this -1 being distributed to this fraction is going to flip the fraction. So this is just going to turn into 2 plus 6, because that would turn into 2 over 1, which is a whole number. So our y-intercept for number 2 happens to be the same. It's going to be 0, 8.